So now we'll need to start the third part of the lecture. And I understand that many of you didn't have time to finish the third task in the first part, so the on-screen digitizing. So make sure you do that later in the tutorial session, because that's something you will be assessed on in the project and also perhaps in the final exam. So pay extra attention to the third task in, I think it's 1C, is it? So create a polygon for the lake based on the Tasmania map. And also you will have other exercise in the tutorial session on on-screen digitizing. So pay attention to this, because this is something you will be assessed on in the project. All right? So now I'll need to carry on and talk about the third topic today. So the third topic is spatial data editing. All right, now try to pay attention to my slides and presentation, because this is important for the rest of the exercise. All right, thank you. So in spatial data editing, here we're trying to remove errors that happens when we import and transform the spatial data. So what's the difference between spatial data transformation and editing? So in transformation, we're trying to fix systematic errors. So the errors may occur in all the data features. But in spatial data editing, we're trying to deal with or correct individual errors. So this error can be in the location data. For example, the vector data, they're not properly connected. Or it can be a topological error, meaning that it violates certain topological rules. Remember when we talked about the vector data in last week? There are different topological relationships between vector data: adjacency, containment, and connectivity, right? So actually the topological rule can be defined more explicitly, and we'll talk about that later in the end of this lecture. And we'll also have arrows in the attribute data. So remember, what is attribute data? We have the spatial data representing the shape and location of the vector features. But we also have attribute data attached to this spatial data. So they can represent, for example, the use of the land or the owner of a house. All of this information in a tabular format are attached to the spatial data. So we can also have errors in the attribute data, or we have outdated attribute data that we'll update. So this can all be done in the spatial data editing task. And let's start with editing individual features. So there are many tools built in ArcGIS that allows us to edit the individual features. And we can use these tools to basically correct the errors shown here. If we have a spike on the lines or undershoot, we can extend the line to meet the other line. Or we can close a polygon, for example. So in the first task, you will be using different tools to edit the individual features. So this is very straightforward. And the next one is edit features with shared geometry. Because with vector data sources, usually we have the feature that shares the same geometry. So that is called coincident. So the features can be coincident. And when we update them, or when we edit one part of the geometry, we want to update the other features simultaneously so that we can keep the topology or let the features continue to share geometry. So this is done by a map topology. So remember we talked about last week, the map topology is used to describe how the points, lines, and polygons share coincident geometry. It can be in one data layer, or it can be the shared geometry on different data layers. So for example here, if we look at the figure to the right, we have a polygon representing the forest. And then the stream, or the hiking trail, is sharing the boundary of the polygon, right? So now if we change the polygon for the forest, the hiking trail or the stream should also change along if they are attached or if they share the same geometry. So we can use the map topology to define the relationships between geometry or features. And if we have the topology, then when we move a vertex, we know that these three edges share the same vertex. So when we move the vertex, you can see all these three edges are moved together with the vertex. So there are different topology types dealing with different feature classes, points, lines, or polygons. So there are 6 basic types. The arc node topology. So basically defines that the line feature can share endpoints. And region topology, polygon, node, route topology, and point event. So these are basically the common sense, right? But we somehow need to embed this common sense so the computer program can understand it. So it understands what topology is and how different features share the geometry. So when we build a topology, it's very important to understand what parameters in the topology. So there are 3 parameters. The first one is cluster tolerance. So this cluster tolerance basically defines the distance at which all vertices or boundaries are considered coincident. So taking this one as an example, if we have 2 edges, and then the vertices of them, the distance between these 2 vertices are within the cluster tolerance. So now they're considered coincident. Now if we validate the topology, it will basically connect these 2 edges with the same vertices, with the same vertex. Okay, so that's how cluster tolerance works. And the second parameter in topology is called ranks. So for example, here, when we move this vertex, you see all these 3 edges are moved along, right? So how do we determine which edge should move when we move a shared geometry? So this is defined by the ranks. The ranks define the level of features and the relative motion of the feature when we do the validation or when we apply the topology. So you can consider ranks as the level of priority. If a certain feature has a higher rank, it means we are trying our best to preserve its location and shape. So if we look at this example to the left, we have different edges here. And if we want to validate the topology of these features, then basically we want to connect these edges. And you can see the vertices of these two edges are falling inside the cluster tolerance. So meaning they will be snapped together. But in this case, how do we determine whether we want to move this edge with these two border edges, or we want to extend the border edges to the thin edge? So this is done by the ranks. So if we give the border edges a higher rank, then the system will basically first crack this thin edge, create a new vertex, and distort or bend the thin edge to connect with the border edge, with the edge with higher rank. So here is another example. If we have three edges, if they all have the equal ranks, then you can see the movement of these edges are averaged. So all these three edges are moved or cracked to link together. But if we have a higher rank for the horizontal edge, then you can see the vertical edges are moved to match with the higher rank feature. And if we have a higher rank for the vertical edges, then the horizontal edges are cracked and snapped to the vertical edges. So this is how the ranks work in topology. Now topology can be used to define the shared features or define what happens when we move the shared features. And we can also use topology to identify topological errors in the data feature. So this is done by defining the three parameters: the cluster tolerance, the rank, and here we also want to define what topological rules we want to use. So in ArcGIS, there are 32 topological rules that built in the program. So they usually cover most of the arrows we may want to use. But we can also define our own topology in the program to fit specific tasks or projects. So in this case to the right, we're trying to apply two topological rules. So one is that the building should not overlap the parcels. And if we have this rule, and then the program will identify the violation. So basically, now this building is overlapping with the parcel boundary, and this should not happen. So the program will return this arrow and also suggest how this can be fixed. Another rules used here is the lot line should share the coincident geometry with the lot polygon. So that's a violation here. So this is how we use the topological rules to basically do some reasoning to identify errors defined by the user. Okay, so this is not strictly so this depends on how our problem is formed. For example, here, if we look at a few examples of how these topology rules are applied. If we look at this part, so each of these topology rules are defined in each of these boxes. And on the top right corner, This symbol here means this topology is applied to polygon. And if you see a symbol like this topology applies to the interaction between points and polygon. So this basically defines how the polygon should contain points. So if the point is not within the polygon, then this is the arrow. Okay? So you can see all these topology rules should be applied in different scenarios based on the source or the nature of your data. And let's look at another example. So this one. So this one is the interaction between points and lines. So in this example here, the problem is to map out the location of water quality monitoring stations. Based on the common sense or the context of this problem, we know that these stations should locate along the river, right? So if we have a point representing the station that is not on the line representing the river, then that's an arrow. So we can use this kind of topological rules to identify arrows. So in this case, we can use points must be covered by line. And if there are any points that are not covered by lines, then it's an arrow. So there are 32 built-in topologies we can use, and we should use them in different scenarios depending on what relationship or topological relationship we want to examine or want to identify from the data set. So we talked about the arrows in location, in topology, and there are also arrows in the attribute data. So as I said, the data may be outdated, or there are arrows when we input the attribute data, or simply because the attribute data, the level of detail is not enough for us to solve a certain problem. So we want to, for example, correct the attribute data or include new attribute data. So with the GIS tool, we can add, delete, or updating the attributes. And the attributes are organized in tables in the GIS software. So for example, in this case, we will have the zoning purpose for this parcel. It's either commercial or residential. So we can add more data, link another table to the existing table so that we can get more insight of the property of the spatial data. So now the first exercise in this section is to try different editing tools in ArcGIS. It will allow you to move, split, smooth, reshape, or rotating the geometric features. Or you can extend and smooth the feature. And the second task is about the topology. So we will have a town map, and by building the topology of the map, you'll be able to move a shared geometry, for example, a vertex, and see how the parcel edges are moved together with the vertex. And the third task is to use the topology rules to reason a certain data set. And here you can define by yourself different rules. Try to use different ranks and different topological rules. So in the instruction, you're not given what rules you want to use specifically. So you can try different rules and see how the result will be returned to you. And the last exercise is about attribute data. So here we have the attribute data of the soil type classes attached to this polygon, these polygons feature data. And now we're trying to include new information about the soil fertility classes. So in this exercise, you will link a new table to the existing table and visualize the data for soil fertility classes. Okay. So, okay, I also want to talk about, okay, before I let you guys work on the exercise, I want to talk about the final exam. I got a few questions about what's the format for final exam. So the final exam will have two components. The first one is hand drawing. So you will do something similar as you do in the first project. I cannot tell you what view you will be drawing, but make sure you review all the different views, projections. And the second part will be computer-based. So the whole exam will take place in the computer labs here. And you'll be using AutoCAD and ArcGIS. And it will be very much problem-driven. So you will not be assessed based on all these theories, but these theories are very important for you to understand what function you should use to solve the problem given in the exam. Okay, so in the exam, you'll be given a very real-world problem, and together with the data needed to solve the problem. And you'll be told what kind of results we're expecting. Based on the lectures and exercises, you should know what function or what analysis you want to run to get the expected results. So next 2 weeks, we're talking about spatial analysis. So that is the main part where you'll be using different analysis tools to solve problems and provide the results. But like I said, pay additional attention to the on-screen digitizing. So you'll probably see that task in the project and the exam as well. So if you didn't have time before to finish the exercise 1C, make sure you finish that. And also in the tutorial session, I think the first task in the tutorial session. All right, any questions? Okay, if not, use the rest of the time to finish the exercises in the third section.